So I am grateful to Lasse, who really helped me with my talk, because he really introduced a lot of concepts that will appear here and that probably I will not have time to explain so detailed as he did, and therefore this will be good and helpful for you, I hope. But the news is that I will be introducing one more element of confusion, if you want to, for those not used to transcendental dynamics, and it's that I'm going to go beyond the entire transcendental world to the meromorphic world, right? So this is like if you had a class on polynomial dynamics and suddenly somebody came and said, now let's look at rational maps, right? And you're like, oh, things can twist and, you know, switch, and poles are there, and I can be sent to infinity, with the difference that in rational dynamics, if you're sent to infinity, who cares, right? And here you do care, and things happen. Okay? So this is the first talk, I think, in meromorphic maps. But let's start, well, I just will go through this very, very quickly, because we've been hearing about this. But let me say then that when you look at transcendental maps, you are just thinking of the presence of an essential singularity, or more than one, but let's say one for this talk. And therefore, you can either be talking about entire maps or meromorphic maps. And meromorphic maps means that the poles are there. Not just one pole, not very important, at least one pole that is not omitted, which means actually that the pre-images of infinity are there to stay, and they are like infinitely many of them, and etc. Okay, so this is when I talk about meromorphic maps, that's what I mean. And I want to just make this comparison that I just was saying, right? So polynomial maps are just very special rational maps where infinity is omitted. So meromorphic maps, entire maps are just this very special class of meromorphic ones for which infinity is omitted. Okay, so it's really the same comparison, just put the degree up to infinity. Okay, so again, I know it's too late to start defining the Fatou set, but there is a difference here, right? So the Fatou set will be this maximal open set where the iterates are normal, but previously you need to ask that they are defined. Okay, so in here, orbits, this is the essential difference with everything we've been talking here. Orbits can be truncated. So if an orbit eventually bumps into a pole and therefore to infinity, that's it, because infinity is not in the domain of the map, because it's an essential singularity. So orbits can be finite, end abruptly at infinity, and then there is no normality to talk about. Sorry, somebody? I don't have a dynamical what? Somehow I don't have a dynamical system. Yes, I'm not iterating from C to C or from C hat to C hat. I'm iterating from C to C hat. So, and iterates are not anymore in the same class. I agree.
Philosophically, this bothers me. Okay, for the others too, it bothers me we don't have a dynamical system. Somehow it seems not to matter, but do you have some wisdom to share so I don't get bothered? I have sleepless nights on non-dynamical systems.
I don't know if I can help you to sleep, but I can just try to convince you in an hour that there is a million interesting things that go on in this non-dynamical system, okay? Okay, so the Julia set, I also wrote it here. It's still the complement of the Fatou set, but there are more characterizations of it. So these poles, which are very abundant, they are actually always in the Julia set, obviously, right? And dense in the Julia set. So you can also characterize the Julia set as the closure of the poles and pre-poles, etc., etc. Right? So that's why I gave this slide. Again, singular values here, probably I can just jump over this because there's nothing new, in the sense that singularities, place points where not every branch of the inverse is well defined are still the closure of the critical and asymptotic values, and we've been talking at length about this. So I'll just say that some reflections to do for those that are not used to thinking this class of non-dynamical systems, right? So if you are entire, infinity is always an asymptotic map. So you could think of entire maps as those for which infinity is omitted, but as a consequence of this, infinity is always an asymptotic value for the whole. So as long because an asymptotic value, remember, it's like a point where somehow morally all the preimages or most of the preimages are at infinity. So this is exactly what's happening. Exactly like for rational maps, right? And polynomials, it's like suddenly all preimages of infinity are concentrated at infinity, and this is morally the same. But if you are meromorphic, then infinity might be just a regular point in the range of the function. Okay, so it could have perfectly defined branches of the inverse around every pole and be absolutely irrelevant somehow, except that it's not in the domain. For example, if there are multiple poles, then its infinity is a critical value, right? Because that branch, the branch that takes the neighborhood of infinity to the neighborhood of the multiple pole is not well defined. It's a D to 1 map where D is the multiplicity of the pole. Okay, so just let's get used to these differences with the entire maps that we are all more familiar with. For example, so Lasse started saying, how come we haven't looked at the exponential? Well, if we wanted to do the same, we would say we have to look at the tangent map. That's the example on meromorphic functions, right? The tangent map, the tangent family, it's an example where infinity is never an asymptotic value for any value of lambda, okay? The asymptotic values, so this is a function with two asymptotic values. It's like the simplest you can think because on top they behave symmetrically, right? And the two asymptotic values are located at plus and minus lambda I. So that's like the model, if you want to, for meromorphic maps. And let me give you another example, however, which is, okay, doesn't want to come up. Actually, it doesn't want to move. What happened? You don't know. Okay, me neither. So the other example is this family of functions, for example, e to the z over 1 plus lambda e to the z. This is a meromorphic family, but observe that for a certain value, so in this family, infinity, again, is not in general an asymptotic value, but when lambda, this is defined for every lambda, but when lambda is 0, then this is the exponential. So it's exactly, so although for this value of lambda, this function has become entire instead of meromorphic. It's like all poles have concentrated at infinity. So it's a family, a natural family, in which for one particular parameter value, infinity is an asymptotic value, but for the others, the asymptotic value, which is 1 over lambda and 0, is just moving on the plane as usual. So we are going to restrict to the Spicer class, but in this case, the finite type meromorphic maps. Okay, so as Lasse pointed out, this is a very natural class to study where you can actually prove things, and because precisely parameter space is tractable, right? So lambda exponential or lambda tangent are examples of finite class maps, and in fact, the reason why we are one of the reasons why we will be concentrated on finite type maps, so number of singular values finite, is that all the asymptotic values so singular values cannot accumulate one to the other. In particular, asymptotic values are isolated. So isolated asymptotic values imply this logarithmic behavior. So in the following sense, right? So if I have an isolated asymptotic value and I take, think of 0 for the exponential, okay? So I take a neighborhood of it, what I will get is like a simply connected set, unbounded. So this is, for the exponential, this would be the left half plane, right? Such that the map from this tract to this neighborhood is infinitely to 1. It's a universal covering. And this in reality, well, as just a universal covering means that this is morally a half plane, conformally equivalent to a half plane, which we know maps like the exponential to infinitely to 1 to this disk. So this is the behavior that we have to think about surrounding any asymptotic value that we may have. Okay, and this is a good property to have when you want to do S. Okay, so this talk is about parameter space. So we haven't talked about parameter space in 3 days, right? Why? Well, Lasse today made a very philosophical observation about this, and he's totally right. So parameter space is difficult. So, well, we haven't even talked about the Mandelbrot set somehow, right? Amazing, imagine, and now I'm going to go who knows where. So, so here I should have put the Mandelbrot set as the left picture, right? But anyway, in rational dynamics and in polynomial dynamics, we understand very well the Mandelbrot set, or even a cubic parameter space of cubic polynomials somehow, or even for some rational maps or rational families. So in transcendental dynamics, there's also, as Lasse pointed out, you have to start somewhere and build from down up, right? And many, many one-dimensional slices have been understood or explored or looked at or worked, right? So especially the exponential parameter space is quite well understood, this family e to the z plus lambda. We observe fundamental differences with polynomials, right? So hyperbolic components are unbounded, for example. And then there is this Cantor-Bouquet structure for which the singular value escapes to infinity, and that's also similar or reminds us the structure on dynamical plane, etc. And in the meromorphic world, I would definitely think of the tangent slice as the one that is best understood. And we see, again, fundamental differences with the exponential family, because many, many hyperbolic components are, everything but 2, are bounded actually, and although the structure is the same, so the multiplier map is a universal covering, so it's again infinite degree. So let me just, I will forget many names, but if I think of a parameter space of entire functions, I would think of Baker and Ripon, and then Eremenko and Lyubich, which we will talk about in a second, and the thesis of Lasse Rempe and Dirks, and well, many other people that have been looking at this parameter plane for one or other reason, and maybe Linda Keane and Janina Kotus, who did this very systematic study of the tangent space. But not only these two are maybe the models, right? But then many other people have been looking at different slices for different reasons, because, you know, to add critical points, families that have some interest or novelty and show new phenomena that have been appearing in the different studies. So the one attempt at generalizing some of these features could be, it's contained in this recent work with Linda Keane, where we looked at hyperbolic components. Not really hyperbolic components, but anyway, the components that are generated by the bifurcations of the asymptotic value in some particular, what we call dynamically natural families, which means basically that only one singular value can be bifurcating at the same time. So in this case, we looked at these components that we call shell components. So this would be for the exponential, and this would be for the tangent, for example, or for these one-dimensional natural families, dynamically natural families. And it was observed, as in the examples, the existence of these, what we called virtual centers, right? And this is basically, so if it's only an asymptotic value that is in this basin of attraction, there's no critical point, so there is no natural center. But when you converge to this special point here, the multiplier of the cycle is tending to 0. So that's why it was called virtual center. As opposed to rational maps or to polynomials, these points are on the boundary. Okay, they are on the boundary, on the bifurcation locus. So this is it was an attempt at generalizing some of the features that had been observed in the different slices. But in this talk, I want to take a more general approach, and I want to look at it in a more global way, right? So I want to present, by the way, it was in the initial slide, but I want to mention it aloud. This is all joint work with Anna Benini and Mathieu Astorg, and this is pandemic work, okay? So it's been done by Zoom we've had a lot of fun with it. So, yeah, and it's also work in progress. So there is one preprint in the archive, and a new version will come soon, and it's still ongoing work. Okay, so we would like to think of in a little bit more global setting, and the global setting was just set up for us by Lasse half an hour ago. So we will, oh, it's not here yet, sorry. So we want to look at the bifurcation locus. We'll see in which family in a moment, but we would like to study the set of stable parameters. So think for a moment on structural stability, but actually you can think of here's the definition of what do we mean by J stability, the same that you would say in rational dynamics, which means that you can follow the Julia set around. So parameter values for which you can find a neighborhood where the Julia set can be followed. For example, if you are inside a hyperbolic component, right? You should think. So if this approach, this very global approach of taking a natural parameter space and trying to understand J-stable parameters, which are the stable equilibrium, the parameters for which if you kick a little, everything stays the same somehow, right? Under perturbation. This was successful at the beginning, at the 80s, for families of rational maps. Or if we think of transcendental world, for the natural families that Eremenko and Lyubich defines. This is exactly what Lasse was explaining. So given a function, you can embed it into a natural family of the quasi-conformally equivalent functions to the one you are starting with. And this can be given a structure of, if we are in finite type, this is a finite dimensional manifold. Okay? So this is the natural parameter space where you want to be working on. So we would think of these quasi-conformal homeomorphisms to be holomorphically depending on the parameter. And this means we will think that this one at least needs to fix infinity. So the essential singularity keeps at infinity all the time. And at the parameter lambda 0, we just have the identity. And this means that the critical values of your family and asymptotic values move holomorphically with the parameter. They cannot collide. That's why it's a natural family, because you keep constant the number of singular values and the type of the singular value. Okay? So when I say successful, I mean the theorems that we all know and that were the very first natural questions to ask, right? So if you take one of these natural parameter spaces, rational maps of degree D, where are these stable dynamical systems? And they proved, Magnez-Sullivan and Lyubich for rational maps, and then the generalization by Eremenko and Lubitsch, which, sorry about the years, but there are 2 papers, and one is in Russian, and then there is the translation, and I will write indistinctively. I just realized 85 and 90. So basically, the big theorem is that these J-stable parameters are open, form an open and then set in the parameter space where you are looking, right? So this result is related to the activity or passivity of the singular values. And what does that mean? So we will say that the singular value is active if, when you consider the family of iterates as a function of lambda of this singular value, either it's not defined, that's for the meromorphic case, but in the case of rational or entire, it's simply not normal in any of the neighborhoods, right? And if this happens in a non-persistent way, we will say that the singular value is active. So, as you very well know, the classical theory gives a lot of characterizations of J stability. And you can prove, therefore, that J stability is equivalent to having passivity of all the singular values. So all these families of iterates as functions of the parameter, they are, so everybody behaves, all the singular values behave in the same way if you modify the parameter. That's what morally this would be, if you perturb slightly the parameter. And at the same time, this is also, and this will be important in a second, this is also equivalent to not creating any new attracting cycles. So attracting cycles not being born or disappear. Right? So the number of attracting cycles needs to be constant in this neighborhood of the parameter that you are considering. And here you could put 1 million more equivalencies, but I want to concentrate on these 3. Okay, so as I said, this was first established for rational maps and then generalized for natural families of entire functions. So what are the obstructions that would prevent you from following the Julia set? So being J-stable, so following holomorphically the Julia set is more precisely stated as having a holomorphic motion. So you have like an injective map, right, that takes every point of the Julia set for a given, of the base point for the base function. For a given parameter, you can map it, and this is injective, to the corresponding point of the Julia set of F lambda, right? So you can holomorphically move every point on your Julia set and respecting the dynamics, which means that really in the neighborhood where there is stability, there is conjugacy. There is a quasi-conformal conjugacy. So this is really, because of the lambda lemma, this is enough. It's equivalent to being able to follow periodic orbits. So repelling periodic orbits are dense in the Julia set, and the lambda lemma tells you if you are able to follow this dense set in a holomorphic way, you can follow the closure, which is the Julia set. So really the key point of all this is, or the key point in order to be able to follow the Julia set in an injective holomorphic way with respect to lambda is really that the periodic orbits stay distinct, right? So in rational maps, the only obstruction for this holomorphic motion, for this following of the periodic orbits, is when they collide. Because you live in the sphere, and holomorphic orbits cannot go anywhere. They are there all the time, right? The only problem is that, you know, they are moving and they can bump into each other, creating a parabolic cycle, right? So that's clearly the obstruction for these holomorphic motions to exist, this collision, right? But in the presence of an essential singularity, so in entire maps or in meromorphic maps, a priori, there is a way to exit the domain, which is that this periodic orbit could be happily disappearing into infinity, one of its points or all of its points in the cycle. So they could be exiting the domain because there is an exit door, which is the essential singularity, right? So it turns out that, well, let me just give you a precise definition of how we would formally state this disappearance to infinity. So a cycle, we say that a cycle exits the domain or disappears into infinity if you can find a curve of parameters converging to a particular parameter value, finite, in the domain, in the manifold or in the parameter space, such that one of the points in a periodic cycle that is moving nicely with this lambda of t parameter satisfies that the limit is infinite, right? And in fact, this picture is very enlightening, but you need like 1 minute to reflect on it, right? Many of you have seen it already, of course. But basically, you can draw this in the following schematic way. You could think here of your compact connected manifold, your parameter space in the x-axis, and then you can think of your dynamical plane on the y-axis, and you could draw these PNs, these manifolds, right, which are basically these pairs of parameter, value, and variable for which z is periodic of period. It's fixed for f lambda to the n. And you could think of this projection map, which is this map that projects onto the first coordinate. So you could so the idea is that as long as I can follow this leaf of Pn in this part, for example, without colliding with anybody, this is okay. So this would be corresponding to a regular value of this projection map. So if I take a lambda over here, sorry for the, so maybe I'll do it with this mouse. If I take a lambda over here, I can find univalent branches of the inverse with no problem. But if I take this lambda c over here, there is one branch of the inverse which is not well defined. This is a critical value of pi 1. And if I take this lambda 0 over here, again, this branch is not well defined because this Pn just escaped to infinity, right? So this is the formal way one can think of critical values of pi 1 for collision of periodic orbits, asymptotic values of pi 1 for cycles exiting the domain. Okay? Good. So example, so can actually cycles exit the domain? So yes. For example, lambda z plus e to the z, not of finite type. I'm cheating, but it's just to illustrate it easily. When lambda converges to 1, which is a very normal parameter, all fixed points disappear to infinity. They are gone, right? Because e to the z equals z. Did I do this wrong? Lambda tends to 0, excuse me. When lambda tends to 0, right? No. What am I saying? No, it's correct. It's correct, excuse me. Okay. So what was the main theorem in the paper of Eremenko and Liubich where they studied these finite type classes of entire maps? The main theorem there was to say for entire families, for natural families of entire maps like the exponential or any other, right, in any dimension, cycles cannot disappear to infinity. In other words, the main theorem was stated as pi 1, this projection map, only has algebraic singularity. So no asymptotic values for the projection map for general natural families of entire maps of finite. This was really the difficult theorem there, the very nice and strong result, which by the way, we believe that the proof applies for bounded type 2, but I'm not going to get into this. So that was really the key issue in order to prove that the theory of Magnès-Sullivan could be carried with no problem, because this phenomenon was not existent for entire maps. However, when you are in a family of meromorphic maps, the ones with poles, these phenomena do happen. does happen, excuse me, okay? So if I have at least one non-omitted pole, so when the poles are there, one of the consequences of poles existing in there is that they actually can provoke that cycles disappear into infinity, so that this projection map has asymptotic values, and then everything changes radically. Okay? So the first thing we make sure of, it's not difficult to say that that's it, no more surprises. So if you look at meromorphic maps, either you have to be worried about collisions of orbits, about cycles disappearing into infinity, or accumulation of these phenomena, parameters that but that's it. Okay, so these are the two things that you have to worry about and no more. And then, well, we started thinking of how these would affect to this goal of proving that indeed J-stable parameters are still open and dense in the meromorphic world, right? Because this is really an essential and fundamental difference in the proofs of this type of result. So here is another character in this play that will play a role. Excuse me for repeating. Okay, which is another special one that is inexistent in other situations. This is what we call the singular parameters. Okay, so you could have a parameter value for which a singular value, right, simply bumps into a pole. Okay, so coincides with a pole or pre-pole. So you could have a parameter value lambda 0, and one of the many asymptotic values or critical values simply after any trace is mapped to infinity, so truncated orbits. So these are parameter values with truncated singular orbits. We call it singular parameters because we didn't find a better name, and I know it can be confusing, but try to keep with me. So critical parameter, if it's a critical value that has this problem, asymptotic parameter if it's an asymptotic value, the one that is shot to infinity in n steps. Okay?
Sorry, just one question. So you always have the non-persistence. So
yeah. Because if this happens for all lambda in your manifold, then this is not singular. Singular implies exceptional, right? And if it's just happening for every lambda, then these parameters value, so there's nothing special about lambda 0. That's what, nothing singular about lambda 0. Yeah, that's non-persistent. Okay? Yes, exactly. And that's why I'm adding it all the time, because every phenomenon that I mention really needs to have this there, or there's no activity, no. Okay, so singular parameters obviously belong to this activity locus, right? Because if you have a parameter that is singular, the orbit of the singular value is truncated, so there's no hope that there will be any stability in a neighborhood. So every singular parameter is an active parameter value. For every singular parameter, V lambda is active for that parameter value, obviously, right? So this is like immediate just from the definition. And in fact, these special parameter values that are non-existent, I repeat, in the world of entire or rational dynamics, they are one more of these classes of parameters which are actually dense in the activity locus. You can prove this, or even, and interestingly, critical parameters, so when it's a critical value, they actually can be approximated by centers, pure centers, so parameter values for which the critical point is periodic. Okay, so they can be accumulated from, they are limits of hyperbolic parameters. Not really hyperbolic, because remember, we are not, the word hyperbolic shouldn't be said because there could be many other parameters doing many other things. So this, by the way, I mean, the usual techniques of applying Montel's theorem don't work because of this truncation. So really you need to do some kind of a shooting lemma or other equivalent tools. Okay, so I just wanted to put one example because Lasse showed so many pictures and I don't have many, but I think it's not really to fix ideas because it's not easy, but I just want to show you how it looks, one of these parameter spaces. This is a one-dimensional family. The theorems I'm presenting are for arbitrary dimension, but this is one of the families that we studied in our work with Linda Keane. This is a dynamically natural family, and I think it's cute, the fact that since it has this particular property that so it has one asymptotic value and one critical value, right? And because of the way it's designed, they cannot bifurcate at the same time. So here, basically this green region is when the basin of 0 captures everybody, and then in here, the critical point bifurcates, and out there, the asymptotic value bifurcates. So when you make a blow-up of this region here in the middle, you get this. And what is this? Well, this is your critical value doing what critical values do, right? They bifurcate as in the Mandelbrot set, but they have these extra guys which are the critical parameters, the ones for which the critical point is actually bumping into poles, and they accumulate on the boundary, etc., etc. I'm not going to get into it. Instead, here, so if I blow up this part over here, now it's the asymptotic value which is bifurcating, okay? So here, this is a blow up of this part. The picture before was a blow up of one part here. This is a blow up of this side here, and this is infinite multiplier map with infinite degree, so it's essentially very different from the other one. It's like going from polynomial to transcendental. Okay, I don't have time. I mean, we could give a talk about this family, but this is not the objective, so I will just go on. Sorry? The root here is a parabolic. It's a parabolic parameter, okay? Because the singular parameter is actually this one over here. So you should think of the shell component I showed at the beginning. So the shell, so the multiplier from here to here, it goes once around the unit circle, and then it starts once more and more and more and more and more. So it wraps to here. That's the singular parameter. That's where the asymptotic value maps to a. Okay.
The online participants can't see when you point with the laser pointer.
Yeah, I'm sorry. Yes, you're right. So here, this would be the singular parameter. Okay.
Thanks.
So, thanks, Lasse. Okay, so next character in the play. Well, or at least the next concept. So when I have an asymptotic parameter, right? So a parameter that is eventually mapped to infinity, it gives rise to a virtual cycle. What's a virtual cycle? So let me just put it in a picture. It's an abstract concept as of now. Then we will see how it appears. But it's a sequence of points that are basically mapped by f, except that, of course, infinity is not in the domain. So if one of them is infinity, then the next one, that's the condition to become a virtual cycle. If one of them is infinity, the next one is an asymptotic value, okay? And the previous one is a pole if it's finite. So it could have many infinites, but as long as it's finite, f is acting. In the moment that infinity plays out, so here, for example, we would have a 1 which maps to a pole, then to infinity, then whatever. The next one is an asymptotic value, a pole that maps to infinity, next one an asymptotic value, etc. This is what we call a virtual cycle, and it turns out that, it turns out, obviously, when I have an asymptotic parameter, somehow I can write down a sequence like this, because it's like so I could start here, and then mapping after n iterates to infinity, right? Probably will not have a second loop, but any asymptotic parameter gives rise to one sequence of this type. Okay, so let's just make a quick summary of the new concepts that we've seen, and then our goal will be to relate them all. So we want to relate, on the one hand, singular parameters, so parameters for which a singular value maps to infinity, non-persistently. Active singular values, so parameters for which the iterates of the singular value with respect to the parameter are either truncated or not normal. Cycles disappearing to infinity, right? We've seen this phenomenon, and at the beginning we said we wanted to talk about J-stability. So we want to see how these four concepts relate to each other in this parameter space. Okay? So the first result that I want to point out is that cycles, when a cycle, so the first question that you may ask, so in this phenomenon where a cycle just moves away to infinity, does it need a singular value to help? Can it do this on its own, right? Or do you need some singular value to help in this? So how is the singular value involved in this process of just escaping away? So the first theorem says, well, if a cycle is disappearing to infinity, it can only do it at singular parameters. So at that parameter value, when the cycle escapes, you need a singular parameter to be there mapping to infinity for that lambda 0. In fact, you can be more precise. The cycle that is escaping actually converges to what we just saw, a virtual cycle. Okay? And this virtual cycle needs to contain either an active asymptotic value, so an asymptotic value that is non-persistently mapped to infinity, or an active critical. Okay? Now I want to know how I'm doing with time, because I had this prepared and I just didn't click, so I have no idea. 8 more minutes? Oh my God, so no proof. You have to connect next week to Bedlebo, and I will give some, we will give a 2-part talk, and I can talk about a little bit more about this. So basically the idea is that when the cycle disappears, if you consider this in function of t, no, using the formal definition I gave, in the limit, you must get one of these cycles that maps to infinity and back, and the returning point needs to be an asymptotic value. However, let me say that the hard part of this theorem is really to prove the non-persistence. So seeing that the asymptotic value is there is relatively simple, using this beautiful structure of natural families of quasi-conformal equivalence, but showing that the asymptotic value, this activity is, that this presence, this singular parameter is actually singular, so that it's not persistent. This is the really hard part, and it uses a lot of good ideas from Elemenko and Lyubich in '92, where they really looked at how the function grows on unbounded curves. Okay, so this is, I would say, one of the hard parts of this paper. So I want to notice that it generalizes the entire result, no? Entire as opposed to meromorphic. If the whole cycle in an entire function, the only way a cycle could escape to infinity is if the whole cycle at once is tending to infinity. And then the virtual cycle, the limit would be infinity, 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 infinity. But by this theorem, it would imply that infinity needs to be an active asymptotic value. And for an entire map, infinity is never active, because it's always an asymptotic value, right? So just this proof would generalize, or would include also the entire case. Okay, corollary. So if your family, you can check, and there is no persistent relation of this type, so you have your family and you see that there is no asymptotic value which is persistently mapped to infinity, then you can actually cross out this active critical point, which actually, I must confess, we would like to cross it out always, okay? It's really because we don't know how to do better, and we have to allow for this, but work in progress, we are trying to cross out the possibility that it's a critical point, the one that is provoking all this. We believe it's always an asymptotic. Anyway, this is a technical thing. And let me present you the second main result of this work. And I think this is really very beautiful because it's one of the things that was left open in all these particular instances of parameter spaces of meromorphic family, which is the following, the converse. So now suppose I have an asymptotic parameter. This is something discrete, so you algebraic, you check and you say, okay, for this parameter value, this asymptotic value is mapping to infinity, okay? How does this relate at all with cycles exiting or not, or disappearing or being created? I mean, why should this a priori be related to anything, right? Why aren't these like Mishurevich, right? Why aren't these just scattered parameters in the bifurcation locus, and who cares? Well, it turns out that if I have an asymptotic parameter, at that parameter value, a cycle is disappearing to infinity. This is how you can locate them. Okay, so moreover, and this is, I think, really beautiful, it's like it's not a repelling cycle disappearing to infinity, it's actually an attracting cycle that needs to be exiting to infinity. Which is as to say that every singular parameter is accessible by a curve inside a, I will not dare to say hyperbolic component, but you should, if you happen to be in one of these one-dimensional families where your stability is really a hyperbolic component, this is telling you that if you are one of these asymptotic parameters, remember this is algebraic, just an equation, a singular value mapped to infinity, you need to be accessible from one of these parameters for which there is actually an attracting basis. So from the inside of the stability locus, if nobody else is bifurcated. Okay? So this really proves the main conjecture in our work with Linda Keane, in which we knew that all virtual centers were asymptotic parameters, but not the other way around. It had been observed in other families, but in general, this we didn't know how to do this, and this very general work that we've been doing now really proves this conjecture in much better than expected. Okay, so this really allows me to summarize. Well, this was an idea of the proof, but I don't have time, I think, to go over it. So just let me summarize saying, let's for a moment forget about these persistent relations. Let's imagine that our family has no persistent relations of these singular values being mapped to infinity. So a cycle disappearing to infinity, we've proven that it needs an asymptotic parameter. So the parameter at which the cycle is disappearing is also a parameter for which some singular value is shot to infinity. But we've seen also the converse, right? So if this happened for lambda 0, at that lambda 0, some attracting cycle is just going away with the multiplier. So this is a virtual center. We've also seen that we know that asymptotic parameters are active parameters, right? Parameters for which an asymptotic value is active. And this is, as in Magnès-Sullivan with very little modification, equivalent to J instability. So you cannot follow the Julia set in these instances. Which, by the way, a cycle disappearing to infinity obviously means you cannot follow the Julia set, and this is like this is by definition being in the bifurcation locus. So all these players in this game are related to each other, as I'm showing here, and putting this together with the density theorems I mentioned of these special parameter values, you would have an equivalent or a stability theorem, a characterization of Julia stability for natural families of meromorphic maps. So you would be able to say that J stability is equivalent to every singular value being passive, every period, the number of attracting cycles being constant. There is work in order to arrive here, but basically the hard work are the two theorems I showed you. And also here we should add, and I didn't for any reason, but that cycles are not disappearing to infinity, right? So many of the proofs, in order to be able to prove these equivalents, are fundamentally different from the rational or entire ones, because you have to take these new phenomena into account. And the corollary is that J-stable parameters are open and dense in this very general setting of natural family of meromorphic maps. And thank you for your attention.
So thank you for a nice talk. Any questions?
Sorry? This is yesterday's walk. Yesterday afternoon. Well, in the lunch break.
Question? Oh, sorry.
Yes, a natural family.
Sorry, can you remind me what a natural family was?
Yes, of course. I'm going faster here. So this is what Lasse, it's a quasi-conformal equivalent. One second. Here we go. Okay, so a natural family is a family F lambda that can be written as one for a base point, and then the dependence on lambda comes from these quasi-conformal equivalents. Okay, so this is like, in fact, if you give me one, so the base point is irrelevant. Okay, so if you give me another base point, I can also write it the same. By allusions.
So I guess for your density of stability theorem, it is very important that you know that the cycle becomes this disappearance cycle is attracting near before disappearing. So how do you see that? Could you give us an idea? So how to see that it should be attracting?
Yes, very much. But I have to do this in the blackboard. Well, I think, okay, I can try to do it with this transparency I didn't show. And if not, I can do it. It's better in the blackboard, but they told me not to use it if possible. So here we go. So let's see if I manage. So it's simple. The idea is simple. How to make it work is not, but the idea, the geometric idea, is very simple. So this is your diagram of natural family, right? So here you have your base point, and these are your QC homeos. But actually, you can ignore these if you want. So suppose you have an asymptotic value that is mapped to infinity. Okay, so it's true. So, okay, may I? It's really, so I think the people online should just switch to the blackboard for a second. So suppose you have an asymptotic value, V lambda, which after some iterates, right, it's mapped to infinity. But this is an asymptotic value. So it means that there is a tract here, right, that maps to a neighborhood infinitely to one of these asymptotic values, right? Okay? So, and this is like F lambda 0 to the n that maps it to infinity. And this would be your F lambda somehow, lambda 0 for the tract. Okay, now if you move the parameter, so this is only an idea, because to make it work, you really need to put it into that diagram. But an idea is that once you start moving the parameter, right, this is non-persistent, and therefore this V lambda, the neighborhood of your V lambda, will map to somehow a neighborhood of infinity when you move the parameter. So in your manifold, the first thing you do is to try to find a curve, right, a curve lambda of t tending to lambda 0, for which you are sure that, so this, if you take a curve like that, your v lambda will be moving, so this will be like a curve here, and you want it so that you are well inside, so that when you map by f lambda to the n, you are well inside your track. You can actually do that with your conformal map, that you know you are in the left half plane, and we actually use the negative real line. Okay, so it's a curve of parameters which translates into a curve of singular values. So this would be your v lambda of t, right? Which translates into a curve of f lambda n of v lambda of t. Okay, so it's like everything is here moving the parameter, and of course your map here, then it's lambda of t, right? So everything moves. Now if you do this, now it's when you start building the attracting cycle. So take t close enough to lambda 0 so that everything is very near infinity, and choose a disk, like do it here if you want to, right? Choose a disk on this centered at one of these points. This translates into a disk here, and then the idea is simple. This one iterate, so try to pull back first with the nth iterate of f lambda, and this disk, let's call it dt, will pull back to a disk over here of comparable size somehow. Of course, here you will go through poles, etc., but it's always this expansion due to poles. So in the spherical metric, this is really comparable diameter. However, when you take this last iterate, right, so this disk here, let me make a blow up, right? So under f to the n, it will go to this one that you prescribe. The spherical diameter will be comparable, but in your last step, right, it's really from an exponential track to the asymptotic value. So here you have exponential contraction. So by some careful estimates, you can show that actually you go well inside U. So you've built an attracting fixed point moving continuously with the parameter, right? And this modulus is every time bigger. So it's like this is, as t moves towards lambda 0, your disk is moving more close to infinity, which is saying that this is like going really to the negative part. So this contraction is bigger and bigger all the time. So if t is really close to t0, to lambda 0, this is tiny. And that's why the multiplier is going to 0. More or less.
Okay, any more questions? If not,
I have a small question, maybe not about parameter spaces, but more about the dynamics of meromorphic functions. I'm just trying to imagine, can this happen that almost all points have truncated orbits, so it's really hard to find a point that you can iterate for infinitely long, or?
No, every point in the Fatou set can be iterated infinitely long. You have the same classification theorem, you have Siegel disks, you have attracting basins, you have parabolic basins. So think of the Newton's map of, well, those are not finite type, but they are even worse. So yeah, Newton's map of a sine.
I think my question was whether there is this interesting functions for which you cannot iterate almost anything.
If there are some of those. Because you could take parameters. So if the Julia set is the whole plane, right, then poles and prepoles are dense in the Julia set, so they will be dense in the whole plane. So for all those dense set of parameter values, you have truncated orbits. Countable, that's true. Well, infinite union of countable. Okay.
Okay, thank you. I think that's it. Let's thank the speaker again.